Hi, my name is Caroline Alting, and today I will be presenting Lab 3, Magnetic Field of a Bar Magnet. In this lab, we studied the magnetic field produced by a bar magnet through the use of our smartphones by downloading a magnetometer app, and we determined the numerical factor that the separation distance impacts the magnetic field. We also used the bias-Savart laws and computed values of the distance dependence for the on and off axis magnetic fields. And we also had to compensate for Earth's magnetic north in the experiment. The results of my experiment were that the distance dependence was equal to negative 3.081 meters and the magnetic moment was equal to 1.586 amperes times meter squared. So the physical concepts in this were the bias-Savart laws, because we're dealing with magnetic fields. Also the superposition principles, because we had to adjust for Earth's magnetic north to cancel out interference. Then we also know that the bar magnet is a dipole, and the corresponding magnetic fields to this. And then we used the equation to find the magnetic moment shown there. And then we also used the equation magnetic field of the bar is equal to constants times distance to the distance dependence power. And we also know that magnitude decreases as the observation location is moved further away from the bar magnet, hence the exponential. And the goal of this lab was to find the value for n. So for the entire experiment, we had to download the magnetometer app, and for part 1, we measured at different distances where the magnetic field was equal to 20, 70, 120, 170, 220 microteslas. We also identified the magnetic sensor in the smartphone, and then we found through calculation and putting our data on a graph and finding the logarithmic values of this equation, which will be shown in the next slide, we found the distance dependence and the magnetic dipole. And then for part 2, we found the off-axis at a 45-degree angle magnetic field, and this was done by moving the phone until the magnetic field was equal to 100 microteslas, and then we moved the phone to a 45-degree angle to find the magnetic field. And we used a computational model to compare the predicted and observed 45-degree measurement using GlowScript. So this is my data that I put in the spreadsheet. In the graph here, we know that because the magnetic field is equal to kr to the n power, we can linearize that, and the slope of the line is equal to the distance dependence, which is negative 3.081. Then for the off-axis, we found that the magnetic field is equal to this vector, and that the distance is equal to about 0.284 meters. So these are my calculations to find the distance dependence. We linearized it using exponentials, and the slope of the line is equal to the distance dependence, so therefore n is equal to negative 3.061. And then for the magnetic moment, we can set that the equation kr to the n power is equal to mu naught over 4 pi times 2 mu over r cubed, and this lets us find the magnetic moment is equal to mu equal to 1.586 amps times meter squared. This is my computational model for the off-axis magnetic field. We had to find, we can find the arrows and using the equation shown previously, and this is a visual of my code. This is the cyan arrows are the on-axis magnetic field, and the orange arrows are the off-axis magnetic field, and this is shown by the vector here, and we found that the distance is equal to 0.284, which compared to the computational model is similar. Any discrepancies can be blamed on other electronic devices in the vicinity interfering with the the magnetic field of our bar magnet. So the questions that were asked were, if I hadn't oriented the experiment to compensate for the magnetic north, how would this have changed our results? The values would have been skewed because we hadn't isolated the x component from the magnetic north. And also, if we were to stick two identical magnets together and run the experiment again, how would this differ? The magnetic field would be a little less than double the value of a single magnet, just because there's a greater magnetic field. And this is because the variation of distance r in the calculations. Alrighty, thanks for listening. Bye.